Welcome to this class. या क्लासमध्ये आपण कॅलोरीमेट्री विच इज नथिंग बट हीट एक्सचेंज या प्रिन्सिपल बद्दल स्टडी करणार आहोत. सो लेट अस सी दिस प्रिन्सिपल फर्स्ट. सो व्हाट इज हीट एक्सचेंज प्रिन्सिपल? सपोज आपल्याकडे सपोज हीट रेजिस्टंट बॉक्स आहे. सो वी हॅव अ हीट रेजिस्टंट बॉक्स. व्हॉट इज हीट रेजिस्टंट बॉक्स? जी आतमध्ये हीट आहे, जी ऑब्जेक्ट्स आहेत त्यातले हीट बाहेर सराउंडिंगला शेअर करू शकत नाही, और वाइस वर्सा. जी सराउंडिंगची हीट आहे दॅट कॅनॉट एंटर द हीट रेजिस्टंट बॉक्स. सो आतमध्ये जे काही हीट एक्सचेंज आहे दॅट हीट एक्सचेंज विल ओनली गो बिटवीन द इनसाइड ऑब्जेक्ट्स. सपोज दिस इज हीट रेजिस्टंट बॉक्स आणि याच्यामध्ये आपण दोन ऑब्जेक्ट्स एकमेकांच्या कॉन्टॅक्ट मध्ये ठेवलेले आहेत. For sake of understanding, we are keeping them in contact. In contact, then there is a heat exchange by the process of conduction. Otherwise, there will be a radiation process. Suppose this is A, this is B. या A चं टेम्परेचर, this is heat resistant box. या A चं टेम्परेचर समजा TH आहे. TH हॉट आहे म्हणून TH घेतलेला आहे. B चं समजा टेम्परेचर TC आहे, कोल्ड आहे, आणि TH इज ग्रेटर दॅन TC. समजा याचं मास आहे MA, याचं मास आहे MB. याची स्पेसिफिक हीट आहे CA, याची स्पेसिफिक हीट आहे CB. मग हीट एक्सचेंज इथं काय असणार आहे? हीट रेजिस्टंट बॉक्स असल्यामुळं ॲज टेम्परेचर ऑफ A इज मोर दॅन टेम्परेचर ऑफ B, A will transfer heat to B and B will gain this heat. And there is no other object kept in this heat resistant box. So whatever heat is lost by A, that is entirely gained by B. So this is what the heat exchange principle tells us. So heat lost by hot object is equal to heat gained by cooled object. सो आपल्याला माहिती आहे आता हीट एक्सचेंज, आता हीट किती फाइंड आउट. आता समजा फॉर एक्झाम्पल ही जी हीट एक्सचेंज प्रोसेस आहे ही कधीपर्यंत कंटिन्यू होणार आहे? ज्या अर्थी आपला हा ए ऑब्जेक्ट हॉट टेम्परेचर आहे तो हीट एनर्जी लॉस करतोय, त्या अर्थी हा हीट एनर्जी लूज केल्यानंतर याचं टेम्परेचर डिक्रीज व्हायला सुरुवात होईल आणि याचं टेम्परेचर बीचं टेम्परेचर गेन केल्यामुळे इन्क्रीज व्हायला सुरुवात होईल. अँड दिस विल कंटिन्यू अनलेस द बोथ ऑब्जेक्ट्स टेम्परेचर्स reach to final common temperature T. So this T is common temperature. So TH keeps decreasing until temperature T is reached. At the same time, TC keeps increasing unless temperature T is reached. आणि ज्यावेळेस या दोघांचं टेम्परेचर सेम होईल त्यावेळेस हीट एक्सचेंज प्रोसेस इनफॅक्ट काय होणार आहे? थांबणार आहे. सो जर आपण ए ऑब्जेक्ट जर कन्सिडर केला तर ए चं टेम्परेचर जे आहे दॅट इज डिक्रीजिंग TH टू T, आणि B चं जर कन्सिडर केलं तर दॅट इज इन्क्रीजिंग TC टू T. सो दिस इज इन्क्रीजिंग, दिस इज डिक्रीजिंग. सो हीट लॉस्ट बाय ऑब्जेक्ट A which is hot is mass of A, specific heat of A into delta T of A. This must be equal to mass of B, specific heat of B, delta T of B. And now we'll consider this delta T to be positive, delta TB to be positive, because we are particularly mentioning heat lost and heat gained. That's why. Therefore, so what happens here? So MaCa, what is change in temperature for A? TH is greater, so that's why we'll write TH minus T. This is very important. You should not write final minus initial all the time if you are writing particularly heat lost and heat gained. If you are writing only heat exchange and you are not worried about who is losing the heat and who is gaining the heat, then you can simply write T minus TH plus MbCb T minus Tc, and that must be equal to 0. But we are particularly writing lost equal to gain. That's why TH minus T, and this must be equal to, this is MbCb. And now in case of B, this T temperature is more than Tc. That's why we'll write this as T minus Tc instead of Tc minus T, right? So this is the difference. Okay, no worries. So we know the masses of all objects, specific heat of all objects, and initial temperature of hot object and cold object. And from this, we can figure out what will be the final temperature of both objects. So from this heat exchange principle, we'll be able to figure out till what temperature they will keep exchanging the heat. That's what the heat exchange principle tells us. And this heat exchange principle is basically used in calorimeter to determine the specific heats of unknown objects. That's what we learned here. So similar thing, the similar heat exchange we can apply to heat exchange processes, which include even a phase change process. So let's see how we can do that. Okay. So let us consider. So we have seen the heat exchange, this heating curve basically. So that heating curve is okay. Let's look at the heating curve in brief. Let me draw directly a curve without. So this is a rise in temperature. This is constant temperature process, which is nothing but heat. Sorry, phase change. Again, rise in temperature. Okay, let's not worry about further part. Okay, fine. Here, let's say this is, let's take an example of water itself. So this is ice. This is water. So considering the melting point of ice to be 0 degrees Celsius at point A and at point B. So at A, we have ice at 0 degrees Celsius, and at point B, we have water, but still at 0 degrees Celsius. Because this AB process and this AB, which connects these 2 points, is basically a phase change process. This is a phase change process. So this phase change for pure substances occurs at constant temperature. That's why this temperature remains constant at 0 degrees Celsius. And somehow we have reached point B, where we have entirely converted ice into water, but still we have this water at 0 degrees Celsius. Now again, if we start hitting this particular water at 0 degrees Celsius, now it will keep increasing its temperature unless it reaches its boiling point, which is 100 degrees Celsius. And let's say if we have reached here somewhere where we have reached boiling point, C. Okay, so at C we have a temperature of 100 degrees Celsius. Now still we have a water. So at point C we have a water at 100 degrees Celsius. Cool. Not cool actually, it's hot. And now if we start heating again, we will move on horizontal line, which is a constant temperature line, because now our process of phase change started. Until point D, which is at still 100 degrees Celsius, but at point D we will have a steam. So that's what we will convert entire water into steam at a constant temperature of boiling point equal to 100 degrees Celsius, and at point D we have a steam at 100 degrees Celsius. We have a steam at 100 degrees Celsius. So these processes AB and CD, these are called phase change processes. AB and CD are called phase change processes, and these occur at constant temperature. This is very important point. So for pure substances, we'll take this phase change processes to occur at constant temperature. So let us see by looking at the example. Okay, so let us take an example that we have a ice, 1 kg ice. Let's take an example. So we have a 1 kg ice at minus 10 degrees Celsius. And now let us mix it. Let us mix it with 4.4 kg of water. Let us mix with 4.4 kg of water at 30 degrees Celsius. 30 degrees Celsius. And let's see what happens. So what do you think? We have ice, which is at minus 10, solid state. We have a water, liquid state at 30 degrees Celsius. Now, there will be heat exchange because this is kind of hot object for us and this is kind of cold object for us. So it will keep losing its heat to cold object. That's why its temperature going to decrease and this temperature is going to be increasing. Okay, and somehow they will meet at certain common point at which the process of heat exchange stops, and that would be the final temperature of the mixture. So this is kind of mixing problem. So this is a mixing problem, and we have to figure out what would be the final temperature. All right, no problem. So if you look at this particular configuration of the mixture, so you have here ice, one object, some minus 10 degrees Celsius. Then you have some water here at 30 degrees Celsius. Okay, and this is at minus 10 degrees Celsius. So this will keep exchanging the heat. And what happens now? what happens? This will start increasing the temperature. It may come here, and now this process is phase change, which is at constant temperature. This is decreasing, it will come down, maybe somewhere here, we don't know. So we have to see what happens actually. So what happens? So suppose if I figure out ice, let me take out first ice. So I can distribute the entire process into three parts. This is temperature rise, this is phase change, and this is temperature fall. So let me take first ice, and which is rising the temperature from 0, so minus 10 degrees Celsius to 0 degrees Celsius. What is the heat required? So heat required is mass of ice. Mass of ice 1000 gram. It is 1000 gram. Specific heat of ice. This is important. Specific heat of ice. You must know this. Specific heat of ice is approximately 0.5 calorie per gram degree Celsius. So let me use this value 0.5 into, I'm changing temperature from minus 10 to 0. So rise in temperature is 10. So if you find, this is 5000 calorie. This is 5000 calorie. Okay, all right, no problem. Let me take out now water. For water, I am losing out the temperature. So let me take first from 30 degrees Celsius to 0 degrees Celsius. So this process, temperature fall process. Okay. So what is the heat required? Again, mass of water 4400 gram. Now specific heat of water. Specific heat of water, you must know. Specific heat of water is 1 calorie per gram degree Celsius. So this is 1. And fall in temperature is 30 degrees Celsius. So if you multiply this, what would be the value? This is 132,000 calorie. So if you look, if you want to bring this ice from minus 10 to 0 degrees Celsius, you would need to provide 5000 calorie. And if you want to bring this water from 30 degrees Celsius to 0 degrees Celsius, you have to take out this much calorie of energy. So you can see here. So water is able to give us this much amount of energy, but to bring the ice from minus 10 degrees Celsius to 0 degrees Celsius, we need only this much. Okay, so there is third one. There is third one. What is that third? And this third is nothing but phase change. This third is nothing but phase change. Phase change. Okay, so phase change. So what is the heat required in phase change? We know this is simply mass multiplied by latent heat. So what is the mass? We have taken ice. Ice is 1000 kg, 1000 gram. 1000 gram multiplied by latent heat. Now we must know again the latent heat of fusion of ice, fusion melting of ice, and that is equal to 80 calorie per gram. So if you want to convert the ice, 1 gram of ice into water at constant temperature, let's say 0 degrees Celsius, you have to provide 80 calorie. So this is 80 calorie. So how much? This is 80,000 calorie. So now look at these three types of energies. So this is energy lost by water. This would be gain, and again this would be gain, because this is ice, both are ice. So total gain, if you look at total gain energy here is what? So total gain is 80 plus 5, that is 85,000 of calorie. And if you see total lost by water, it's still 13200. So which is greater? So this is greater. So I can conclude that this water still has more energy than what is required by ice to come from minus 10 degrees Celsius to 0 degrees Celsius, again phase change to this point. So this 85 is for, let me denote this point P. This is energy required to come from point P to point B, still here, because we have considered this temperature rise PA. So this is a process PA. This phase change is process AB, and this is for, let me denote this Q. This is for QB, right? So this 85,000 is from P to B, and this Q to B, Okay, Q to B, and which now I can conclude that QB still have more heat than what is required for PB. So in fact, our final temperature would be somewhere here, so that 85 plus something, and this is 132 minus something, so that they'll balance here. And at some point, let's say denoted by X, I have a common temperature. Till that, we have heat exchange process going on. So what is that final temperature? Let's figure out. So I have explained the principle. Now let me figure out this temperature. So finally, let me write this. Ice, we are starting from minus 10 degrees Celsius, then we are reaching out to 0 degrees Celsius, then again we are reaching out to 0 degrees Celsius. So this is temperature rise. So this is phase change. And again, finally, we are reaching out to T degrees Celsius. So this is the scenario for ice. And what is the scenario for water? So we are 30 degrees Celsius, and simply we are coming down to T degrees Celsius, and this is temperature fall. So let me write this process on the diagram. This, then phase change, and that's this. So let me denote these points: A, B, C, D, and this is D point because T degrees Celsius, and let us see, this is E. So A, this is B, this is C, this is some D, and this is the final one, which, sorry, this is D, and this is E. This is E. So we are coming from this side, water, sorry, ice. Here we had water, and again here. And from this, we have this. So here we have ice. Here we have ice. From 0 to 0, still we have ice phase change. But from 0 to T degrees Celsius, we have a water. We have water. And here we have water. That's what we write here. So this must be equal to this, right? So let us write down. So for AB process, so let me write AB plus BC plus CD. This must be equal to process ED. So AB is what? AB is what? AB is temperature rise. So MC delta T. MC delta T, mass of ice. Mass of ice 1000 gram. Into specific heat 0.5. Into temperature rise 10. All right. Plus BC is phase change. Phase change mass of ice 1000. All right. Multiplied by latent heat 80 calorie per gram. That's it. Plus CD. CD is now 0 to T. And now it is water. But which water? The water which is formed from ice itself. This water is different at E, which we have 4.4 kg. And this is what we have 1 kg. And here we are increasing the temperature in process CD of water which is formed from this 1 kg ice. That would be 1 kg only. So this is M. C of water, it's, sorry, we are writing in gram, that's why 1000 into specific heat of water 1. And now rise in temperature for CD process, T minus 0. So this is T. This must be equal to ED. ED is what? Now ED, for ED we have 4.4 kg of water. So that's why 4400. Specific heat of water again 1. And now fall in temperature is, now E is more and D is less. So let me write it like 30 minus T. 30 minus T. So that's it. We have to simplify. Divide by 1000 everywhere. 3 zeros cancel. 3 zeros cancel. 1, 2, 3 zeros cancel. So it will become 4.4. And now if I figure out this, so this is 5 plus 80, 85. 85 plus T. And this will give me 4.4 into 30. So this is basically 132 minus 4.4 times T. And if you solve this, you take it out here, this would be 5.4 times T, which is equal to this, you take out there. So 32 plus 15, this is 47. So finally, T would be 47 divided by 5.4. 5.4. So you approximate this. If you double this, 94. If you double this, while approximating, if I consider 5.5, if you double it, it would be around 11. And now it is approximately 11, 8, 88 plus 6, some 8.5. So final temperature would be around 8.5. So the temperature of this point D would be approximately equal to 8.5 degrees Celsius. So this is how we are supposed to solve the examples on heat exchange. We must figure out first till what point it may reach. So it may happen that it will reach only till this point on the process of phase change itself. We never know. We have to figure out that first and then proceed further. So while figuring out, you can directly start from this step itself, but while figuring out, if you may see that heat loss is sometimes less than heat which is required for gaining, and that time you must need to stop on this line itself. So let us see such kind of example one. Okay, so next example, we'll see this. Okay, so in this example, we have a 10 gram of ice. So let us 10 gram of ice at 0 degree Celsius and mixed with 10 gram of water plus 10 gram of water at 10 gram of water, which is at 20 degrees Celsius. And this is again a mixing problem. And now we have to figure out final temperature. We have to figure out final temperature. So again, so I have 10 gram of ice at 0 degree Celsius. So I am already on the phase change process. So I have here 0 degree Celsius. Let us denote this point A. Now this is horizontal at 0 degree Celsius. And let us say my phase change process ends at point B. So this is still water at 0 degree Celsius. And now I have up here, I have another C. This is 20 degrees Celsius of water. Now I'm mixing. So this curve is going like this. And if I mix it here, I may end up somewhere here. I may end up somewhere here. These are the two possibilities, right? So I have to figure out. Okay. So one process is AB, another process is CB. So let me write this down. AB is phase change process. Phase change process. And what is heat required in AB process? Heat required in AB process is ice, melting of ice. So this is 10 gram multiplied by latent heat. Latent heat is 80. So this is 8,000 calorie. So if I want to bring this ice, 10 gram of ice from 0 degree Celsius to point B, I must gain 8,000 calorie of heat energy. Let us look at the other process. On the other hand, we have 10 gram of water. So water is going to lose its energy, heat energy, and it will keep on decreasing its temperature. So let us consider CB process. So CB is nothing but temperature fall process. So in temperature fall process, heat in CB, heat lost in CB process is equal to mass. Mass 10 gram of water into C specific heat of water is 1 into fall in temperature. From C to B, it is 20. So what is this? This is only 200 calorie. This is only 200 calorie. So what happened here? Which energy is more? So if you want to take your ice from 0 degree Celsius to, let's say, B point for the entire phase change process, you have to gain 8,000 calorie of energy. And if you want to decrease the temperature of your 10 gram of water from 20 to point B, you have to lose only 200. So this 200 is not sufficient to provide this 8,000. So it will keep on decreasing till here. It can only lose 200, which would be gained by ice, but this is not sufficient for ice to reach out here. So as this is more, this is less, we may end up somewhere here. So here, let us say somewhere here. So this temperature would be 0 degree Celsius because this is phase change process. And now we end up at point D. So we have to reach from A to D and from C to B to D. This is the heat exchange route. So from ice perspective, we have to reach from A to D. But what happens from A to D? Only few, among 10 grams of ice present, only few grams of ice must have melted till this point. Remaining, it's still water, right? And like this. Okay, so this is the water. And water, we have to come from C, then will reach to B, and again to D, again to D. So this is the route along which heat exchange will take place. But our question is final temperature. So what would be the final temperature? So final temperature, as we are ending on a phase change process, so final temperature would remain at 0 degrees Celsius. So final temperature would be 0 degrees Celsius. So this is what we must understand in the principle of heat exchanges, right? So this is all about this. So you must be able to figure out what temperature would be the final mixture will reach, and so on. So towards the end of the lecture, let us briefly discuss about Newton's law of cooling, and then we'll conclude. Okay, let us briefly understand. We are not going to use it, so it might be useful somewhere in other chapters or even in mathematics. Newton's law of cooling. So what is Newton's law of cooling? Suppose if you have a hot object. Suppose if you have a hot object at let's say theta degree Celsius. Let's say theta degree Celsius. Hot object. Obviously hot in the sense as compared to ambient temperature. So let me denote ambient temperature as well. So ambient temperature. So ambient temperature, let us say this is theta naught, theta 0 degree Celsius. So we know this hot object is going to decrease its energy and its temperature is going to fall. And with respect to time, if I differentiate this, if I look at the rate at which this temperature is falling, so I can denote this by d theta over dt, d theta over dt. And we know as, so this is the Q heat exchange is mc delta theta. So though I denoted by theta, you can sometimes write as a T only. So it's a matter of representation of your variables. Okay, Q mc delta theta, and heat is going to decrease. So delta theta at all times, so at certain temperature, instantaneous rate is given by, this is m, this is specific heat, and this is what? This is this theta, delta theta, change in temperature, temperature of object at that time minus ambient temperature, minus ambient temperature. That is what we are going to write it here. So this d theta over dt is proportional to difference in temperature of that object and ambient temperature, temperature of an object and ambient temperature. So from this proportionality, we write this equation as d theta over dt equal to some constant of proportionality times theta minus theta naught. Now, if you look at here, as our object is hot, this heat exchange will keep on going unless this theta reaches to ambient temperature theta naught. So that's why if you look at this particular quantity here, this is all the time positive quantity because theta is more than theta naught ambient temperature. This is positive quantity. If you look at the left hand side, so let me take this proportionality constant to be positive again, k. And if you look at the left hand side, so this is d theta over dt. So as my time is proceeding, so this dt is, let's say, positive as we are proceeding in time. So this d theta is in fact decreasing. So this is negative. This is negative. So to accommodate this, we have to put a sign over here, negative. Just to mention that with respect to time, as time proceeds, this theta is decreasing. That's why we have used negative sign. So this is exactly kind of radioactive decay process. And this differential equation can be solved like d theta. So I can take this here. So 1 upon theta minus theta naught d theta equals to minus k times dt. And now if I integrate this plus constant of integration c. So I can say that integration of this is ln of theta minus theta naught equals to minus kt plus c, minus kt plus c. And at time t equal to 0, if I take some temperature or something like that, you can easily find out. Or even if you can write this as theta minus theta naught equals to e raised to minus kt plus c. You can take out this e raised to c separately into e raised to minus kt. And you have to use initial condition. So what is initial condition? So initial condition is at a time t equal to 0, starting the process, you must have the temperature of object to some temperature. What should we denote? Theta I. Let us denote theta I, initial temperature. So this equation basically becomes anywhere, we can put it even here. So this C equal to, so this KT at t equal to 0, this term will vanish. This is ln of theta I minus theta O. So if you put at here, you get ln theta minus theta naught equals to minus KT plus ln theta I minus theta naught. If you take it out here, if you use the this thing and all, you'll be able to find out. So this you can simply define as, or even e raised to c. This value is here. So e raised to c is e raised to ln of theta I minus theta naught. You can use here. This is base is same e. This is theta I minus theta naught. So you can use it here and you can simplify this term. So this is theta equal to theta naught plus e raised to c is theta I minus theta naught multiplied by e raised to minus kt. E raised to minus kt. So this is the temperature of your object at any time t. At any time t, where this theta naught is the ambient temperature and theta I is your initial temperature. So this, let me denote it theta I, and theta is instantaneous temperature at any time t. So basically this is Newton's law of cooling. This is important. This principle is important. The rate of fall of temperature at any time is proportional to difference in the temperature of object and the ambient temperature. From this, you can set up a differential equation and solve it properly. You'll get the final expression for temperature at any point. So at any time t. And this law, this proportionality law, is valid for small difference of temperature of object and surrounding. So this is not generally valid for where the temperature difference between object and surrounding is very large. The point to remember this. So this is all about Newton's law of cooling. So this is how we have concluded this part of lecture. So in the next part, we may even discuss further examples.